Good morning, everyone, and welcome back to Computer Systems. Today we're going to go through a deck of slides on file systems. This is another deck of slides from the set of slides I stole from Krista Wilson 5 or 6 years ago. So this may have some stuff that's slightly out of date, but we're mostly looking at the design of historical file systems here. So all this data should be perfectly valid for what it's talking about. Last class, we talked about hard drives and solid-state drives. We talked about how they work, and the important thing to remember from last time is the sort of interface that we got to build on top of. So hard disks and SSDs give us sort of an array of blocks. They give us two sort of API operations. We can read a block from disk. To do that, we give a logical block number, probably a 64-bit integer, to the disk, and then after some amount of time it will give us back one disk block. And a disk block is usually 512 bytes or maybe 4K on a more modern system. Oh, and if you hear thunder in the background, that's because I'm recording this during a thunderstorm, so that's fun. But yeah, two API things. We have read, which translates a logical block address into a block, and we have write, which takes a logical block address and a block and eventually tells us it successfully wrote. And the important thing about blocks is that historically they're 512 bytes, but in modern systems sometimes they're 4K. So the first thing that we need to talk about before we get into the details of how file systems themselves work is to talk a little bit about partitions and mounting. After that, we're going to go through the sort of really old historical DOS file system, the FAT file system, and then we're going to look at the sort of still standard Linux file system, ext4. But to get to ext4, we have to go through the historical file systems, which were the previous versions, which go all the way back to the extended file system. So first, partitions and mounting. Now, when we boot up a PC, one of the first things that the firmware needs to do, whether that firmware is BIOS or UEFI, is it's going to have to scan all the disks, and for each disk, it's going to have to check all the partitions on that disk. Now, a partition is just logically splitting up a disk into multiple sort of logical disks, and that's something that PCs have supported for forever. In fact, in the traditional master boot record structure that we have on hard drives, the first block of data on the disk, that's going to be the first 512 bytes, provides space for 400 bytes of bootstrap code, so that's going to have to be code that executes and can find and load the bootloader. That takes some trickery, but that's not the problem we're trying to solve right now. The other thing here that is in this 512 bytes is hard-coded space for 4 partition entries. So we can split the disk up into as many as 4 partitions. There's ways to do extended partitions, which let us go over that limit of 4, but the master boot record has space for 4. And that could look something like this. We could have a machine set up to dual boot Windows and Linux, and so we have 2 Linux partitions, one regular partition, ext3 for storing our Linux data, and then we have a swap partition. We know why we need that. And then we have 2 additional partitions for Windows. We'll have our NTFS partition, which is the modern modern Windows file system, at least for desktop Windows. And then we have a FAT32 partition, which is the old sort of Windows 95 era Windows file system, or DOS 5.0 file system, which it turns out still gets used for a bunch of stuff even today. Another option is that we can just have a disk with only one partition entry in the master boot record, and that results in us being able to use the whole disk for one thing. Here we have one big NTFS partition, which should be a reasonable way to partition a system that is only going to boot one version of Windows. Now, if we want to have more than 4 partitions, we can have one of the partitions be marked as an extended partition, and then within that extended partition, we get a sort of extended secondary partition table, and that lets us have a whole bunch of partitions if we want on this style of partitioning. On PC systems, and that includes PC systems that are running slightly less common operating systems like FreeBSD, they have different partition table formats. I think on FreeBSD they use a a disk format called slices, which has some other set of limitations for how partitions are set up, and then you have some questions about do you nest slices under MBR partitions if you want to multi-boot Windows and BSD, but luckily, if you have to deal with those problems, then you get to figure them out, and until you have to deal with them, you don't have to figure them out. Now, the first file system that we need to mount when we boot up a system, so we've had the firmware loads the operating system kernel, and then the operating system kernel is going to start booting, but it needs to get to data on disk in order to be able to do the boot process. For a modern Linux style system, the minimum thing it's going to need to do is load that executable to start init, the first user space process. And so we want to be able to read that init executable off disk. And to do that, we're going to have to follow a path. We're going to have to do directories and file names to find that thing. And so that means we have to have somehow organized the different disks and partitions available in our system into some sort of file system structure. We have a choice as to how that works, sort of design-wise. And Windows and Linux do it different ways. On Linux, every single thing is going to be mounted under a single hierarchy. So the first partition we mount, the root partition, its root directory is going to be called /. And then if we have some other partition mounted as like our home partition, then file system paths under /home are going to be on that partition, but things under /temp will not. On Windows, the sort of normal view that you get for what's going on is that every device that you're going to have is going to be assigned a drive letter. And that actually, unusually, this usually isn't how Windows and Linux come out as far as user interface design. Unusually, this exposes the technical detail of which disks are what to the user, which might actually be a good thing on Windows, where if you have a your default hard disk is going to be the C drive. You put in a floppy disk, that's the A drive. You put in a CD, that's going to be like the E drive, or here in this picture, it's the H drive. And so it's clear to the user what data goes on which disk. Whereas on Linux, you have to understand what the convention is for your particular distribution. And there isn't sort of a clear drive letter that shows you which thing's which. If we look at a list of partitions on some concrete computer, this is Christo's computer from 6 years ago. We might have, in this case, we have two drives in this system. We have the primary disk drive, which is SCSI disk A. We're seeing 4 partitions from it, numbered 2, 4, 5, and 7. So there's an SDA1 partition that we're not seeing here. And the root partition for this Linux machine is SDA7 mounted on root. We also have SDA5 mounted on media CBW data. We have SDA4 mounted on media CBW Windows. I bet that's his Windows partition. And then we have dev SDB1, which is a different disk mounted at media CBW something. I don't know what this is, but it could be another hard disk. It could be like a DVD that was only formatted for 1.9 gigs. It's a second disk. In order to mount a file system, the kernel needs to know what disk device it's trying to mount and where it's going to put it, either what path on Linux or what drive letter on Windows. Once it knows that, it's going to go ahead and take a look at that device, do whatever hardware interfacing it needs to do with that device, and it's going to get the super block for the targeted file system. Usually that's the first block on the partition, but it doesn't necessarily have to be. And that super block is going to contain metadata about the file system. Things like where the data structure is, what version of the file system is, how big does the file system think it's going to be. Once it's found the super block and figured out where it's going to go, it will then configure the mapping so that future references to that drive letter or that path will go ahead and access the data on that particular file system. Now, on Linux especially, there's a bunch of different possible file systems that any given disk could be using as their format. We have the ext series of file systems, which are probably the most common disk format for hard disks on Linux. We have all the Windows disk formats, which we want compatibility with. We have alternate Linux file systems like Btrfs or XFS or RiserFS was an old one that is now infamous. There's a whole bunch of different options. If we want to put in an old CD into our system, then that's a different file system itself called ISO 9660, I think. And so what we want to do is we want to abstract away the disk format from the API to access things. So like list all the files in the directory is something that we want to be able to do, and we want there to be a POSIX API that a user program can call to list the files in a directory without having to worry about how files are actually represented on disk. So we need this abstraction layer, a virtual file system interface, to go in the middle there between the POSIX API, which is what we expose to user programs on Linux, and the file system format implementation itself. And every operating system is going to have to deal with this because at minimum, you have to support CDs, which are their own thing. So it looks kind of like this. We're going to have some processes. Those are going to talk to this virtual file system interface. These arrows are probably system calls. Then the virtual file system interface is going to talk through another interface to these drivers. And then the drivers are going to actually do the hardware calls out to the hardware to get access to the data on disk, whether it's a hard disk or a USB disk, whatever. And most of this file system implementation is going to happen in the operating system kernel. As with any abstraction, the benefit here is that processes don't need to know what's going on in the implementation, and the implementation doesn't need to worry about what individual processes are like trying to do. Also, if we want to add another driver, the sort of structure for how to do that is well defined in the kernel. Now we have to mount file systems every time we boot up a machine, and there can be multiple file systems, especially if they're multiple disks, but we also have to mount file systems every time we add a new disk to the system. And today the most common example of this, still, even though these slides are kind of old, the most common example is plugging in a USB disk. When we do that, we need to figure out what drive letter or path is going to get associated with it. We have to figure out what the file system that is on that disk is, and we have to mount it somewhere. So we do that. Most modern operating systems will do that automatically when you stick the USB disk in. It'll figure out what it is and pick an automatic place to put it and maybe pop up a window to show you the files in it. But there's some assumptions that we make about file systems that don't necessarily make sense for removable devices. And that produces this amusing situation where we sometimes have a button in a file manager or operating system shell that allows us to safely eject a device. On a Mac, that used to be dragging the thing to the trash can before you, and that would cause CDs to eject and stuff. I assume you can still do that with USB drives. But the purpose for this mechanism is that one of the things that we do with file systems is we cache data that's written to the file system in memory. Memory is drastically faster than disk, and that's especially true for removable devices, which tend to be relatively slow. And so we have a performance benefit from caching to memory, but that means that if we just yank out the disk without making sure that we've flushed those caches, the data that we wrote to disk may not actually have gotten written to disk. And so the safely eject button allows us to make sure that we can get the performance benefits from caching. We don't have to turn caching off, but we also can force the cache to flush so that the write actually happens. All right, so that was sort of the intro. Next up, we're going to talk about the FAT file system, but that's going to be the next video segment. See you in a second.